In this video, we're going to summarize everything that we've learned about in this course in four equations. These are called Maxwell's equations. They were developed over a long period of time, and they describe all of electricity and magnetism, which is this classical theory of how charge, electric field, and magnetic field sort of interact with each other. It's a theory that applies in lots of places. It applies at the astronomical level. It applies down to the microscopic level. It's really stood the test of time, and it's quite useful in a lot of different spaces. So the four equations that we're going to talk about in this video start with Gauss's law. So this is this surface integral of the electric field. It's related to the total enclosed charge divided by epsilon 0. And Gauss's law is a statement that if you have charge, if you have some net charge, it will generate an electric field in all of space. It's something that we observe, and it's codified in this equation. Now, there are other ways of generating electric field, and we discovered that if we take the line integral of the electric field, that's related to the magnetic flux and how that changes with time. This was called Faraday's law. So there's two sources of magnetic field, namely that there's some charge that could generate electric field, and there's also magnetic field which can change with time, and that can generate what we call a non-coulombic electric field, an electric field that isn't the result of charge specifically, but rather how the magnetic field changes. What's really important about Faraday's law in practice is that it's the way that we are actually using a lot of new electronics are designed. So if you've heard of wireless charging, or if you have an electric toothbrush that you don't have to plug in, it actually exploits this Faraday's law result, namely that you can change a magnetic field and drive a current and thus charge something without actually connecting it physically. The third equation is Gauss's law for magnetic field, which is a little bit different than Gauss's law for the electric field in that it's equal to 0, which means that there is no such thing as a magnetic monopole. That is, there's not a single sort of lone magnetic charge. If there were, this would not be equal to 0. The total magnetic flux in some closed volume could be a non-zero number, but it turns out it can't. Meaning that if you have a magnet and you break it in half, you'll still have a north and south pole. If you break that in half, you'll still have a north and south pole. And as far as we know, all the way down, you still have north and south poles. Now, this is an active area of research. People are looking into this and trying to figure out, is there such a thing as a magnetic monopole? Was there one in the early history of the universe? And there's a lot of work being done on this to try to understand why this seems to be the case. We don't seem to be able to find one anywhere. Now, the last thing that we have here is the relationship between the magnetic field and the current. So if we take an integral of the magnetic field along some direction, along some path, we'll find that that is equal to the total enclosed current times mu naught. So this is Ampere's law, and it tells us that the current, a moving charge, will generate a magnetic field. And that can be a source of magnetic field throughout all of space. The other thing that we have that is associated with the magnetic field through Ampere's law is a change in the electric flux. So it turns out that if you start to vary the electric field and you produce a changing electric flux, you can also drive a magnetic field. So this gives us a nice parity between Ampere's law, Faraday's law, and Gauss's law, namely that charge produces electric field, changing magnetic fields produce electric fields, currents produce magnetic fields, and changing electric fields produce magnetic fields. The last two of these, that the changing electric field and changing magnetic field produce each other, is really important because that actually tells us about the propagation of electromagnetic radiation, or light. Without this sort of relationship, that is that the magnetic field, a changing magnetic field will produce an electric field, and a changing electric field will produce a magnetic field, we couldn't have this sort of like free-form propagation of light. There'd always have to be some source, some current or some charge that continues that propagation along. But really what it is we can drive with a current or with a moving charge, we can create an electromagnetic wave, and it will propagate in space even though there are no charges or currents to continue its movement. Now, one thing I would mention about these equations is that they're all classical equations, meaning that when they were developed and when these models were analyzed, there was no real thought about what we would call quantum mechanics. So when we start to look down at the really, really tiny level, when we start to try to understand what's happening with atoms, electrons, subatomic particles at their level, these equations are not really describing those situations. We actually have to reformulate electromagnetism in a way that helps us to describe the fact that energy is now quantized. That is, that there are varying steps of energy. So you might remember this from chemistry and thinking about electron orbitals or things like that. So these really apply at that micro scale and above. If we start to dig down even deeper than that, we actually have to reformulate electromagnetism in a quantum way. But these are super powerful. They work over 25 orders of magnitude. We can really understand lots of important physics through them. And in particular for engineering, for most scales, they're actually really important.